Scott Kovach from Stanford University will talk about index streams, formal intermediate representations for fused contraction programs.
Thank you. Hi, everyone. I'm Scott, and today I'll be talking about our work on index streams, which are a formal representation for doing reasoning and compilation of sparse tensor algebra and relational algebra. So first I'll just mention that nowadays programming languages inspired by linear algebra and declarative languages like SQL are widely used pretty much everywhere, whether you're doing high-performance computing or small-scale data manipulations or embedded computing, you're feeling the influence of these languages. And to give a couple examples, on the left I have some matrix operations written in one flavor of tensor index notation. And on the right, there's a SQL query with some joins and aggregates and stuff. And these languages are usually given a formal semantics in terms of tensor algebra and relational algebra, respectively. But there's some pretty cool prior work that unifies the two into this object known as positive algebra. It manages to do this by representing both tensors and relations as a special sort of function. And it does so using only a very small number of operators. So I'll call your attention to the product operation here, which is simultaneously the element-wise product for matrix algebra and the equijoin for relational algebra, and then the summation operator here, which generalizes tensor contractions and also aggregates and reductions for relational algebra. So this is the language we're going to be talking about compiling today. As an example program, we have a three-way vector dot product. So we have three vectors u, v, and w that are being multiplied and then added together. So if you want to represent your vectors using dense arrays and you want to design a compiler that functions in a sort of compositional bottom-up manner, then you might end up generating code like this. So this code first outputs a loop that computes u times v and stores it in a temporary, then computes that times w, and then finally sums up the results. But this program is pretty undesirable because it performs some redundant iterations of the data and allocates a bunch of memory. This program is better because it's fused. It manages to combine all three operations into one traversal of the data. So there's been an enormous amount of research on fusing dense array programs, like this one, but comparatively less work on sparse programs. And we care about sparse programs first, because sparse tensor algebra is a really useful tool, and second, because in order to draw this correspondence between relational algebra and array programming, we really need sparsity to even get off the ground. So just to highlight a little bit why dealing with sparsity is a bit harder, here's a simpler version of the program from the previous slide. But now imagine that the input arrays are stored using various compressed data structures. Then the output code you get is more complicated and also more stateful. So although in recent years there have been a number of projects on doing general purpose sparse tensor compilation and also some work in the database community on fused multi-way joins, there hasn't been much work that tries to get handwritten performance and also formal verification of the output results. But formal verification is pretty desirable in the domains we care about, because we're talking about some critical decision-making applications where a wrong result could be harmful. We're also talking about very expensive computations sometimes that make testing pretty impractical, and maybe correctness checking can also be subtle. So formal verification would be ideal, but as we've noted, the variety of data structures we need to work with complicates things, and the need to fuse programs seemingly requires some sort of global reasoning about programs. But making progress inside a proof assistant requires simplicity and compositionality above all else. So that's why in the work I'm presenting today, we offer index streams, which are an intermediate representation for fused sparse computations that are very composable. And we manage this by actually formalizing those operators from the positive algebra directly as operations on streams. So in this framework, the product of two streams is itself a stream, and that means that it can be composed with others, and a complex expression can be built up out of simpler ones. So our first contribution is a formalization of this theory in Lean and a proof of correctness for the operators. Our other contribution is a prototype compiler called Etch, which combines the operators with some primitive data structures in about a 500 line of code base, and is able to compete with both a sparse tensor algebra compiler, Taco, and also the analytical database DuckDB on some SQL queries. So now I'm going to do a bit of a technical dive into two aspects of the system to try to show you how it works. So first up will be just what an index stream is. So if you've ever written code that traverses an ordered collection data type, you've actually used an index stream, although the interface that I'm going to present today might be a little bit different. So first of all, though, I want you to think of an index stream as a transition system. So this transition system here has 3 states and 2 transitions between them. Each state is also labeled by an index and a value. You can think of these as the output that the system produces as it marches along. So a little more formally, an index stream consists of a state space sigma, 2 functions, index and value, that label states with indices and values respectively. And we typically require that the indexing set have a total ordering so that we can talk about ordered traversals of data. And we usually require that the values support addition and multiplication. We also have a ready function that's binary. And this function marks states that are not ready to produce output yet. So an index stream can go through one or more, you could think of them as internal states before it's ready to produce an externally observable value. And finally, the last component is the skip function. So I've oversimplified a little bit on the previous slides. In fact, an index stream can possess a great number of transitions, and these transitions are parameterized by an index value. This index value tells the stream where it's allowed to go up to, if possible. And we use this generality to handle both data structures that need to go in a sort of serial traversal of their data, but also data structures that support efficient, say, logarithmic or constant time access to random indices. And the second part of this parameter is another binary value that simply tells the stream whether to go up to or just past the given index. And I'll refer you to the paper for some more technical details on why this function takes the shape that it does. Finally, there's an evaluation function so that a stream can be turned into a vector. So you can see this stream produces the values 2, 5, and 3 at the indices 1, 4, and 5. So the ultimate value that you get is what you see here. But streams are not limited to one-dimensional data. As we said, we want to model relational algebra, where tables are usually multidimensional, and database indices are multidimensional, as well as tensors. So for instance, if you want to model this matrix as a stream, what we do is we construct a stream that traverses the non-empty rows, first of all, and then the value function for that stream actually itself yields a stream which traverses the non-empty values for the row. So in this way, you can create arbitrarily nested hierarchical data structures, and moreover, in practice, you can use different data structures for each level, which is necessary for high performance. So the next topic is stream multiplication, because this is kind of the key that holds the system together. So to give some intuition for this, I'm going to talk about merge sort. So if you've seen merge sort, you know that there is a merge subroutine that takes in 2 sorted lists and produces 1 sorted list. And I want you to think about this as a process. The state of the process is represented by 2 pointers, and these pointers can see the front value of each list. And each step, of course, they output the smaller value, and then the corresponding pointer advances. And we just keep marching along until eventually we have 1 sorted list as output and 2 pointers to empty lists. Now, with a very small change to this algorithm, we can calculate the intersection of 2 lists. The only difference is that whenever we're in a state where the 2 values are equal, we output that value, and otherwise we advance the one that's farther behind. So you could say that in that first case, the system is ready to produce an output value, but otherwise it wants to skip the lagging list ahead so that it matches the one that's farther. So in fact, this is this process directly models what happens in the product of two index streams. So if you now think about these two sorted lists as representing the non-zero entries of two vectors, we use the key observation that multiplying any value by 0 yields 0, so that we only need to produce outputs when there's a common value at the same index for both inputs. So in this case, the two streams only share a value at index 2, so the output will only have this one non-zero position. In general, it would be the sum of all the points in the intersection found along the way. And at this point, I just want to reemphasize that index streams can, on the one hand, model input data structures, whether they're compressed or dense or what have you, such as U, V, and W in this example, but they can also model sort of composite dynamic processes like U times V and that times W. So this is the way that we're able to construct one semantic object, which at the end of the day gets turned into a fused piece of code. And our process for doing that is pretty simple. So we use a data structure that contains code fragments or code generating fragments rather than abstract mathematical functions, but otherwise the structure is exactly the same as the model I gave before, the ready function, index value, and skip. And the code generation procedure is actually really simple. If you wanted to burn 5 minutes, you could even write down the whole compiler and it would fit on one slide. And I'll refer you to the paper for details, but part of the reason this is possible is that the compilation is recursive. You can see that the compilation function for a nested stream recursively calls itself. And moreover, if you wanted to extend this procedure, say by implementing a special compilation method for a stream with some special structure, you could do so in our system by just adding a new type class instance. So before I move on to our evaluation, I just want to observe that it seems to be the case that with just this simple combination of efficient data structures and this multiplication operator, you're able to get good single-threaded performance compared to state-of-the-art approaches from both tensor algebra and relational algebra. So I'll refer you to the paper for the full benchmarks. But compared to Taco, we get equivalent generality to the first iteration of the published Taco system. And for the kernels that involve multiplication, we generate almost logically identical code, so we get essentially on parity performance. And then for tensor addition, our system, which is called Etch, uses a slightly slower algorithm. But since the publication, we verified that Taco's algorithm is expressible as an index stream, and we left implementing it to future work. For our relational algebra benchmarks, we took a couple of industry standard queries from the TPCH dataset. These queries involve 6 tables, all joined together with some subqueries and user-defined functions, all of which can be defined easily within the system. And across a range of data set sizes from megabytes to a few gigabytes, we saw a worst case speedup compared to SQLite of 24 and about 1.5 compared to DuckDB, which is a column-oriented vectorizing open source database. These benchmarks are sort of intended as a sanity check that our technique doesn't introduce too much overhead. Etch is not a database management system, so the comparison is Finally, I'll talk a little bit about the correctness proof. So because the system is implemented as a collection of operators all on a single domain, the proof is quite easy to state and relatively easy to prove. So essentially, it boils down to proving this sort of homomorphism theorem. So basically, what we want to show is that the evaluation of the product of two streams is just the product of their evaluations. And similarly for summation and addition, and taken together, this proves that any complex operation, any complex stream computes the correct tensor or slash relation. And in order to do this, we only need a couple of simple conditions on the input streams. So the lawfulness property is essentially that the skip function behaves in a consistent way when it's passed different order sequences of indices and makes progress when it's required to. So one benefit of the system is that if you want to extend it with your own data type, You only need to prove that it satisfies these mild properties, and then it can be composed in arbitrary ways with all the other types in the system. So I'll conclude there, and happy to take questions. Thanks.
Okay, thanks. Thanks. Thanks, Scott. And any questions? Anyone? Okay. So actually, I have a question. So Scott, so when you formalize this thing in Lean, did you use any co-inductive data structures or co-inductive reasoning?
We did not directly because we're mostly interested in finite objects. So we mostly think about things inductively.
Okay, then is there any future direction that if you use a co-induction, somehow you can extend it to infinite thing, which is good or maybe worth? Or
Yeah, I think so. I mean, I would be interested in looking more in that direction. I think there are some definitions we have that could naturally be generalized to infinite streams, like just fine. And we could verify, that any particular stage of progress that the equivalence we want holds. So,
okay.
Yeah, thank you.
Yeah. And any questions? Okay, then, let's thanks to the speaker and let's move on to the next talk. Okay, thank you.